Hello everyone, welcome to lecture 30 of the online course on modern display technologies, flat panel display. Today's lecture will be continuing the discussion on LCD matrices and driving scheme. So here is the lecture outline. We'll be talking about the contrast driving ratio. We'll look into how we can optimize B to maximize the contrast ratio R, the maximum achievable ratio, the voltage transmittance curve, and also the AC waveforms in practice. So let us start our discussion with the contrast driving ratio R. So this particular slide forms the single ratio R equals Vs, okay, over Vns. So you can understand that this R is nothing but the ratio of the voltage of the selected pixel over the non-selected pixel's voltage, right? So you can also see that it is basically square root of b square plus n minus 1 divided by b minus 2 whole square plus n minus 1. Okay, so you are basically dividing the Vs by Vns, okay, and you have this n is the number of rows, okay. These things get into a single dimensionless ratio, that is R. So it is the contrast driving ratio, and you can also see that this ratio R depends only on two things, that is the design parameter B, which we called as a knob in the previous lecture, and the number of rows capital N, okay. So the larger the R is, the better will be the achievable contrast ratio for a given liquid crystal material. So this sets up the next natural question, that what value of B will maximize this R for a given capital N or N. So how do you maximize B, or how do you basically maximize R, okay, by optimizing the B? So what you can do, you can basically, because R is coming as square root of this term, so you can basically go for maximizing R, or even equivalently R square, okay. So when you take R square, the square root term on the right hand side will disappear, okay. So you can take a derivative with respect to B, okay, and that derivative can be set to 0. So that means you can basically set the numerator of this to 0, okay, and you can see that it basically becomes a simple quadratic in B. So how do you find the optimal value of B? You need to basically solve this quadratic equation, b square minus 2b minus n minus 1 equals 0, okay, for getting a physically meaningful positive root for the optimal drive parameter. So from this you can obtain that B equals square root of n plus 1. So this is basically known as the Alt-Plesko optimum condition, okay, and the ideal B basically depends on the number of rows n in the display. So the thing is, you need to understand why you are only keeping this positive root. Since you want B to be a positive number greater than 2 for drive schemes column and row voltages to make physical sense, you have to only go for the positive root solution. And here you can see that the optimal drive parameter is simply obtained as square root of n plus 1, and this is the well known condition, and it only depends on this number of rows in the display. And this single formula is worth remembering, given that you know any passive metric display's row count, you can immediately tell the optimum column or the row voltage ratio that you can use to obtain the best contrast. So you can quickly get an estimate of the parameter B, and that can tell you about the contrast ratio. So how you obtain that? You substitute the optimal B, that is square root plus n, back into your equation of that contrast ratio R, okay, and that gives you the maximum possible voltage ratio that you can obtain from a n row passive matrix, and that comes out to be Rm. There is the R maximum, which is square root of square root n plus 1 divided by square root n minus 1. Okay, so this Rm is the best contrast driving ratio that is physically achievable by this driving scheme for a given n. So no choice of B can do better than this. So you can actually plot this maximum achievable ratio as a function of the number of rows. So here is a plot that shows the maximum contrast ratio as a function of this number of rows, which is varied from say 2 to 100, okay. And if you just recollect, this contrast ratio is nothing but the ratio between the selected voltage and the non-selected voltage, right? So you can see the pattern of Rm. This Rm basically decreases monotonically as n increases. That means with more number of rows in the display, you will get smaller achievable difference between the selected and the non-selected pixel voltages. So what is the physical interpretation of this? Is that with more number of rows, your each pixel will spend a larger fraction of the frame getting exposed to the crosstalk, because crosstalk happens in all n minus 1 slots, okay, where the voltage appearing across it is V over B, okay, and that is relatively that whole thing is relative to only one true addressing slot, okay, out of capital N. So when n becomes larger, that fraction for which it is truly being addressed is basically getting smaller and smaller, and your crosstalk is basically getting accumulated. So this is the fundamental scalability limit of passive matrix addressing, and that is why people got motivated to move towards active matrix TFT addressing. So this particular slide connects the electrical drive scheme analysis of the last several slides back to the liquid crystal material's own optical response. So the figure basically shows the voltage transmittance curve. So here you see for high contrast ratio, the non-selected voltage Vs should sit at or below V10, that is, okay, the 10% of this voltage, of this actual voltage, okay, and then this will be the typical rise time, T min and T max, okay. So we can define this V10 and V90 as the voltages at which the display basically reaches 10% and 90% of its full transmittance swing delta T, okay. So it is basically that one, and it is basically measured from the not the zero level but from the minimum transmission level, okay. So for a good dark state, we basically want the non-selected pixels RMS voltage, that is the VNS, okay, to sit at or below the V10, okay. So it should be here or below this, so the transmittance basically stays as close as to this T min, okay. And given the drive scheme, the best achievable selected voltage is then Vs equals Rm times Vns, okay. So that will be the maximum selected voltage that you can get, because you are ensuring that the Vns is here or below this V10. Now for a good bright state, what you have, we'll separately need this Vs to basically the selected voltage to exceed this V90. Okay, whether it's achievable depends entirely on how steep this liquid crystal's own voltage transmittance curve is. Okay, so normally a gentle or gradual curve needs a much bigger voltage swing to go from this 10% to 90% than a steep one. And if you are having this Rm times Vns, it can't reach this V90, then you will see that the bright state basically comes out dim and the bright state image will look like washed out. Okay, in short, for a bright high contrast image, we need this Vs to be above this V90, that means as close as possible to the maximum transmission Tmax. Now if the Vt curve, as I mentioned, is too gradual, that is not steep enough, in that case your Vm into Vns may fall short of this V90 and you will not get a good image because your bright state is not bright enough. So how do you quantify this voltage transmittance curve steepness? So the steepness of the liquid crystal's voltage transmittance curve can be characterized by the dimensionless quantity gamma. So gamma is basically a ratio of V90 over V10. Now smaller gamma means closer to 1 will represent a steeper voltage transmittance curve. In that case V90 is reached only slightly above V10. Okay, so for a good quality image that has got both high contrast as well as high brightness, that will require this gamma to be less than equal to Rm. So what we understood here is that if V90 is only slightly larger than V10, then your gamma is basically very close to 1. That means your transmittance rises very quickly over a very narrow voltage range. Okay, so your transmittance basically jumps from 10% to 90% and your curve is very steep. Okay, and if this V90 is much larger than V10, then the gamma is very large. That means you have a very gentle or gradual curve. That means you require a very big voltage swing to go from the dark to the bright state. So the key design criteria, which we'll see in the next slide, that can turn into a concrete row count formula also. So we'll see that for a passive matrix display, to achieve both high contrast and high brightness simultaneously, we basically require gamma to be less than equal to Rm, that is the maximum achievable voltage ratio. Now if the material's gamma is too large, okay, as we understand, then too gradual a curve, then for the number of rows in the display, the image quality will suffer. So here we can see that for a given liquid crystal material, gamma is fixed. So if you combine this requirement that gamma should be less than equal to Rm, where Rm is given as square root of square root n plus 1 divided by square root n minus 1, and then you solve for n, which gives maximum number of rows the passive matrix can support, you basically get that n max will come out to be gamma square plus 1 over gamma square minus 1 whole square. Okay, so here 1 over n max is sometimes called the duty ratio of the display. So what you see here is that because of this inverted relation, okay, so it is worth noting for intuition that a smaller gamma means a steeper and better Vt curve will allow larger n max, Conversely, when you go for a larger or more gradual gamma, that forces smaller Nmax. Okay, so this is consistent with everything that we have discussed so far about the steeper curves scaling better. Okay, now we have seen that 1 over Nmax is sometimes called the duty ratio of the display, since it basically represents the fraction of the total frame time over which a single row is actually being actively addressed. Okay, so we'll see the concrete number for a real twisted pneumatic material on this next slide. So for a standard twisted pneumatic liquid crystal display, gamma is actually 1.4. So if you plug in that value of 1.4 into this Nmax equation, which is gamma square plus 1 divided by gamma square minus 1 whole square, you get Nmax to be equal to 9. That means 9 rows is only suitable for the simplest display. Okay, something like the basic calculators. Okay, but you will not be able to take it for phones or laptops or TVs. So twisted pneumatic can be used for LCDs, can be used for calculators. Now this scaling limit is exactly why increasing the VT curve stiffness that we will see in the next slide, and ultimately the active matrix addressing will become essential for the display technologies. So let us take the first thing is the stiffness increase. Okay, so the stiffness or delta V is basically measured by the voltage gap between the saturation voltage and the threshold voltage. So the smaller will be your delta V, steeper will be the VT curve. Okay, and that will give you larger achievable Nmax. So there are basically 3 geometrical or structural layers. So one possibility is that you increase the twist angle, so your threshold voltage will basically rise with the twist angle. Okay, second is you can decrease the pre-tilt angle because your threshold voltage will rise as you reduce the pre-tilt angle, and third one is that you can decrease the ratio of H to P, that means the cell thickness to the cholesteric pitch. Okay, so here the saturation voltage will decrease as the pitch will increase, since your twist elastic energy is basically smaller for larger pitch. So this is how you are basically walking through the 3 geometric or structural levers that allow you to play with the threshold voltage. But one thing important to understand is that none of these levers are basically free. Okay, each involves other material or say optical trade-off. For example, changing the twist angle affects other optical parameters which we covered earlier in the course, but together with the material property levers, okay, they basically represent a toolbox display engineers have used historically to push the passive twisted pneumatic LCD technology, okay, as far as it could go before making shift towards the active matrix addressing modes which have finally become dominant. Now the 3 further levers are also used, which are basically tied to the elastic constants and the dielectric anisotropy. You can increase the ratio of K33 over K11. So the field activated small tilt state basically involves band deformation, okay, and that is absent in the fully saturated state. So your threshold voltage basically rises with K33. Next, you can also decrease the K22 over K11, okay. So the saturation voltage basically decreases with smaller K22. So in the first case, okay, the last method is that you can decrease delta epsilon over epsilon perpendicular. that basically lowers the dielectric torque efficiency that is needed to reach the saturation. So let us go into the details of each of these one by one. So you can see in the first method, increasing K33 relative to K11 basically raises the threshold voltage, because the field activated state at small tilt angle basically involves band deformation that the fully saturated state does not experience. So a larger K33 makes the intermediate band deformation costlier, delaying the onset of switching and steepening the curve. For the second one, decreasing K22 relative to K11 lowers the saturation voltage, helping narrow the gap between the threshold and the saturation from the other side. And the final one that we have seen here, decreasing this dielectric anisotropy relative to the perpendicular permittivity, okay, that means this delta epsilon over epsilon perpendicular also help steepen the curve by reducing the dielectric torque efficiency needed to fully saturate the liquid crystal response. So wrapping up all these three things that you have seen here and the three levers that we see earlier, so together we have seen 6, okay. So the three geometric levers we have seen earlier and the three shown here, these are basically the 6. Together basically it forms a complete toolbox that can be used to steepen the twisted pneumatic cells voltage transmittance curve. So here we will see that a practical detail is essential to every real LCD drive circuit, and why the addressing voltages are always AC waveforms and not simply DC. Okay. So if you recall the LC director's response to an applied field, that basically comes from the dielectric interaction, and the resulting torque depends on the square of the dielectric field. So whether the field points one way or the other doesn't matter for switching. This means that an AC waveform which is alternating polarity in every frame produces exactly the same optical response as a DC voltage of the same RMS magnitude would have done, right? So the question is, why not DC? Okay, a sustained DC bias would inject ions into the liquid crystals, which would have degraded the display over long term usage, and this is why people choose AC with the same mean value, okay, of that DC. So the main answer here is that you are getting long term reliability by using AC, because if you use a sustained DC bias, that will cause the ions within the liquid crystal material to drift and accumulate, injecting them into the bulk, and is essentially that would degrade the display's performance over time. It's a slow and cumulative failure mode. Okay. So AC driving neatly sidesteps this degradation mechanism while still producing the same time averaged RMS driven switching behavior, and this is why every practical LCD type screen, including the one we have just derived, is implemented using the AC waveform in real hardware. So the figure here shows the actual column, row, and the resulting pixel voltage waveforms and the corresponding display transmittance over time. Okay, so here you can see the waveform of the column. So this is the column I, and then you have row M. The voltage is changing with time, the row voltage also changing with time. Okay, and this is the pixel voltage, pixel Mi, for which the transmittance is changing. So these are basically the row M+1 and the pixel M+1 into I, okay, and the study of the transmittance. Okay, so what you are seeing, the leveled voltages in the graphs are basically the voltage of the first half of each AC pulse. Okay, now by varying the column voltage continuously between this minus V over V to plus V over V, rather than the only two extreme values, that basically produces intermediate pixel voltages. Okay, hence the grayscale transmittance levels are created, not just fully on and off. Okay, so here you can see that transmittance level. So if you carefully look into this slide and the diagram, this basically grounds the abstract voltage scheme algebra into a actual timing diagram. So this figure is showing the real column, as I mentioned, column row pixel voltage waveform over time, and also the resultant transmittance. Okay, so this we have already seen. So the minus V over B to plus V over B, this is basically the voltage of the column over different halves of the AC voltage. Okay, and for the next one, the polarity is simply inverted. Okay, so this is the total time frame which is shown here. So far we have only discussed the binary switching. So binary switching means fully selected versus fully non-selected. But if the column voltage is allowed to vary continuously between, say, minus V over V to plus V over V, rather than simply jumping between these two extremes, you can basically get the RMS pixel voltages to take this continuum of the intermediate values. And this is what exactly the real LCDs produce. It can produce smooth grayscale images, not just the black and white ones. Okay, so this figure basically closes out our discussion on the passive matrix methods. So in the next lecture we will basically tune to the active matrix addressing, which will basically solve the problems of the crosstalk and also the row scaling issues in a very fundamentally different way. Okay, so with that we conclude this lecture. If you have got any query, you can drop an email to deb.sikdar@iitg.ac.in, that email address mentioning the course name and the lecture number on the subject line. Thank you.